This video is about series and error. So if we look at this series, 9 plus 3 plus 1 plus a third and so on, that type of series is geometric. And the reason we know it's geometric is because we continue to multiply by the same thing. So our R value here is 1/3. We're multiplying by a third every time. And if we actually calculate these things, we see that the first one ends up being 13, S sub 3. S sub 4, we add an additional term and it ends up being 13 1/3. And if we add one more term, we end up with 13 4/9. This series is said to converge. And so what we may notice about this in part A is that they all appear to be approaching a value. It appears like it's getting pretty close to like 13.5. It's definitely not going to get, well, I shouldn't say definitely, but it looks like it's not going to get bigger than 14. So it appears that not much more is getting added. It's approaching some kind of value where it's not going to go any further. And that means that it converges. So a series converges when an infinite series continues to add up all of its terms and it approaches or converges to a specific value. So now we're going to find the sum of the whole series. So A1 was 9 and R is a third. So A1 over 1 minus R is 9 over 1 minus a third, which is 9 over 2/3, which is the same thing as 9 times 3 divided by 2, or 27 halves, or written as a decimal, 13.5. And we know that this works. The restriction on the ratio that guarantees that it's a finite sum is because the absolute value of R in this case is less than 1, so we know that we're going to get a finite sum. So that means that this infinite series converges, and it converges to a specific value. So now let's take a look at a similar series, except now we're replacing things with variables. So once again, this is a geometric series because we are multiplying repeatedly. So the first term is 1, and it appears that we're multiplying by x every time. So if we're going to write the sum, n equals 1 to infinity, of what's happening, it's just x to the n minus 1, because we start with 1, and then when we plug in n equals 2, we get x, and when we plug in n equals 3, we get x squared, and so on. If we wrote that as a rational expression, that's a1 over 1 minus r, so that's 1 over 1 minus x. So what I can do is I can graph 1 over 1 minus x, and this should mimic what happens when I have this series, because we're claiming they're the same thing, right? So if I continue to do this, it should end up equaling this. So this graph of the red y equals 1 over 1 minus x should equal this thing, because our claim was I can rewrite this as this rational expression. So let's actually analyze whether that's true or not. So what I'm going to do is I'm going to just take this sum. Right now, when a equals 1, all I have is 1. Then when a equals 2, it ends up being 1 plus x, right? You see the line 1 plus x. And then 1 plus x squared. 1 plus x squared plus x cubed. So what we see is, as we add more terms, it appears that this graph of the green line, or the green curve, is staying pretty close to the red curve. And it appears to be staying pretty close to the red curve a little bit longer. Like a little bit longer, a little bit longer, a little bit longer. As I zoom in, it appears to be a pretty good approximation for this for a while, and then it stops. So notice what happens as I continue to add terms. Like if I add a lot of terms, and it takes a while for Desmos to figure it out, but it's still thinking. Notice 37th term, it's going to become a polynomial that goes up. 38th term, it's going to become a polynomial that goes down, and so on. 40th term, it appears that there's a significant breakage in the boundary of when this becomes any good. And it looks like -1 is like when it stops being any good. And obviously, this is going to take a while to think, but obviously it never matches what's happening down here. And the reason it never matches down there is because it's just a polynomial that there's no asymptote in a regular polynomial, no vertical asymptote. So what I have is, no matter what I plug in, it looks like it mimics things. There it only mimics it at one point. There it looks like it's getting a little closer, 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 and so on. But it always appears to be between -1 and 1, where this polynomial looks a whole lot like the red graph. And that's because this only converges when the absolute value of r is less than 1. So if I think about what this worked for, it worked for -1 to 1 for x. Well, what was r? R was x. So that means the absolute value of x has to be less than 1. And if I think about when that works, that's in the interval -1 to 1. So if you notice, we had something that it looked very much like it from -1 to 1, but then never outside. Use the same method from above to determine the rational function that would represent the polynomials below. And so let's see what we have here. A1 is x, and r is 2x. So my rational function is x over 1 minus 2x. And my interval of convergence is going to be when the absolute value of 2x is less than 1. So that means x is between 1/2 and -1/2, or I'll write it in interval notation. Similarly, over here, a sub 1 is 4, and r appears to be x over 8. So my rational function is 4 over 1 minus x over 8. If I simplify this to get rid of the fraction inside of the fraction, I'll multiply everything by 8. So I would get 32 over 8 minus x as my rational function. But my r value in the series is still x over 8, so I can't treat it like what I see down here. I have to treat it like what my r value actually is in the function, or in the series. And so that means the absolute value of x over 8 has to be less than 1, since the absolute value of r has to be less than 1. So x has to be between -8 and 8 for my interval of convergence. Part 4. For the series defined as follows, we're going to do the same thing we did in part 2. So a sub 1 is 1, r is negative x in this case. So my rational function is 1 over 1 minus negative x, which I would write as 1 over 1 plus x. So then I graph this polynomial with the series. So notice if I expand this series out, I end up with 1 minus x plus x squared minus x cubed, and so on. So as I keep adding terms, it appears to be mimicking my graph between -1 and +1. And if I keep adding terms, it's going to do the same type of thing that we saw earlier. So my graph looks something like this: mimics, 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 and then depending on whether I end with a positive leading or a positive, not positive, an even exponent or an odd exponent, it ends up diving one way or the other away at 1. So the interval of convergence is once again -1 to 1. And that's because the absolute value of r, which is the absolute value of negative x, must be less than 1. And that works from -1 to 1. So now this is the sum of an infinite geometric series. We're going to find the first term, common ratio, and first 5 terms of the infinite series. But notice that this isn't written in this form. So what I can do is I can rewrite this in a form that I like. So what I'm going to do is I'm going to do this in 2 different ways, like the directions say. So if I have x over x minus 1, the first way I'm going to do this is I'm going to factor a negative out of the bottom. And notice if I distribute this in, it ends up being x minus 1 again. So this is allowed. So I'm going to rewrite this as negative x over 1 minus x, which is also allowed because I can move a negative multiple on the bottom and put it on the top. So in this case, my a sub 1 is going to be negative x, and my r is going to be x. Just looking at a over 1 minus r, that's what I see. So in that case, I can write the series like this, and my first 5 terms, which disappeared on me, would be negative x minus x squared minus x cubed minus x to the 4th minus x to the 5th, and then I end up with x to the n. The interval of convergence is -1 to 1 because the absolute value of x must be less than 1. Now I can also rewrite x over x minus 1 in another way. I can divide everything by x. So I can rewrite this as 1 over 1 minus 1 over x. In that case, my a sub 1 would be 1, and my r would be 1 over x. And so if I'm looking for the interval of convergence, that would be where the absolute value of 1 over x is less than 1. And that is true anytime x is big or negatively big. So my interval of convergence would be -infinity to -1, union 1 to infinity. So this would be what I end up with. 1 plus x 1 over 1 plus 1 over x plus 1 over x squared plus 1 over x cubed, and so on. And so what we're going to do is we're going to use Desmos in the same way. So the first series that we're dealing with is the one that we claimed was going to work from -1 to 1. So this, we're going to keep adding negative x minus x squared minus x cubed minus x to the fourth, and so on. So negative x, put on a negative x squared, put on a negative x cubed, put on a negative x to the fourth, negative x to the fifth, sixth, seventh, eighth, ninth. And what we're seeing is something very similar to what we've seen a lot of the time, where it looks like it kind of sticks around between -1 and 1. Now, the other one, 1 plus 1 over x plus 1 over x squared, 1 plus 1 over x plus 1 over x squared, 1 over x cubed, 1 over x to the fourth, 1 over x to the fifth, 1 over x to the sixth, x to the seventh, x to the eighth, x to the ninth, x to the 10th, so on. What you see is it's really good everywhere outside of -1 to 1. So it's really good all over here, and it's really good all over here, and then it's really bad where the other one is really good. And so this one, good, 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 oh, turns bad. And then this is good pretty much all the way over here. So if I want to estimate the value at 2.5, I would have to choose a particular series to make it work. And so that would probably be this series, because it's not going to work for the first one. So if I wanted to estimate the value at 2.5, I'd want to choose this series. So we're going to use the sum from n equals 1 to infinity of 1 over x to the n minus 1, because it converges there. So use only the first three terms. So the first three terms would be 1 plus 1 over x, which we're plugging in 2.5, plus 1 over 2.5 squared. And that equals 1.56, which is 39 over 25. The actual value, if I plug 2.5 into the equation here, is 2.5 over 2.5 minus 1, which is 5/3 or 1.33333. The error is what happens when I subtract those things with an absolute value. The error is 0.106 repeating. How many terms would I need to guarantee my error is less than 0.1? If I just add one more term, so I take this and I add 1 over 2.5 to the third, then what happens is my error now ends up being, oh, sorry, this was 1.6 repeating. I think I might have said 1.3 repeating, but 5/3 is 1.6 repeating. So the error then is 0.0426, which is less than 0.1. So that's wonderful. So if I have any more than 4 terms, I have a very small error.